I'm the moderator for today's seminar, and my name is Hang Lu. I'm a PhD from the electrical engineering, and I'm also a member of the Students for Sustainability, known as the S Square at Cost. And I'm glad to welcome you to join our first seminar this semester. And you know, the sustainability seminar series was initiated in March 2020 by S Square with the support of the head of sustainability and the graduate affair at Cost as a platform for raising scientific and the community engagement in the complexity of the sustainability topics. And the topic for today is the journey to the net zero. How far are we? By the incredible Professor Hussein Hoteit. And the Professor Hoteit is associate professor in reservoir engineering, and he is also the program chair of the energy resource and petroleum engineering. His current research includes improved oil recovery, geological carbon dioxide storage, and reservoir simulation. Before joining Costa, Professor Hoteit worked in ConocoPhillips and the Chevron company for about 12 years, where he conducted a series of projects related to the chemical enhanced oil recovery, steam flood, and others. And now please join me welcoming Professor Hussein Hoteit.
All right, thank you, Hanlu, for this very generous introduction. Thank you for inviting me. My pleasure to be here. Can you hear me well, by the way? All right. Well, that's a big topic, right? I'm not sure how I'm gonna handle this, but just back on what Hanlu mentioned. You know, in my background, I really come from petroleum engineering background, so I'm not sure if we are the right people to talk about how to get to net zero. But I'll try my best, and I'll show basically try to be as unbiased as I can towards the oil and gas industry. But let's see how far we can go with this. All right, so this is what I'm gonna talk about. Net zero. We hear about this all the time now. This becomes buzzword. When, where, and why this started. So I'll try to cover maybe some historical background about this, some key landmarks that I find interesting to talk about. And then I will talk about some net zero roadmap that has been sort of announced from some companies. And then I will focus mainly on Saudi Arabia, talking about what's really the scene in Saudi Arabia, what's happening right now. And then I will highlight some of the projects that could be related to this topic. All right. So I try to get back in history to see basically who are the first maybe people and scientists who talk or start to address the issue, right, or the challenge of climate, CO2 into the atmosphere, and the impact of CO2 into on the temperature. And one of the key, of course, scientists is Svante Arrhenius, who he's actually a chemist. He got the Nobel Prize in 1903. And he was one of the first scientists who really could relate or correlate the CO2 concentration with the change in temperature. Of course, he's not the first who talked about this. You know, many scientists, of course, before him, you know, introduced many of the key concepts and sciences behind this. But his main contribution was one of these papers here about the influence of carbonic acid on the temperature of the ground. And what he did there is essentially in this paper he talked about that reducing the CO2 concentration by a factor of 2 or halving the CO2 concentration would increase the temperature by 5 degrees, and the other way around, doubling the CO2 concentration would actually increase the temperature by 5 degrees. But back then, Arrhenius, coming from Sweden, his main concern was actually about the cooling and not the heating of the Earth. And this is one of the statements that he wrote somewhere. By the influence of the increasing percentage of CO2 in the atmosphere, we may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the Earth. So basically, they were like living too much cold weather there, and But basically, he related this also to the increase in temperature, which was interesting. From early 19 towards 1930, maybe not much action happened except wars, right, and stuff like that. But in terms of climate, a guy, Callendar, is one of the young engineers who actually brought something very interesting. He published a few papers. And also he talked about doubling CO2 concentration would increase the temperature by 2 degrees. This is coming from his key paper here, published in 83 or something, 1938. And he's writing here in the summary, by fuel combustion, man has added about 150 million, so we're talking about 150 gigatons or billion tons of CO2 into the air during the first half of century. And then he's saying that the author has estimated that 3/3 or 3/4 of this CO2 stayed in the atmosphere. And he's basically developed the model based on the radiation absorption coefficient and some really very smart calculations. And he came up with this model where he's showing the change in temperature versus CO2 concentration. Now, CO2 concentration, this is in terms of parts per 10,000. So multiply this by 100, this will give you 300 per ppm, okay, parts per million. So this is 300 ppm, this is 200 ppm, and so on. And this is how we're showing the increase in temperature versus concentration. So this brought to my attention just to look more about this model to see, how accurate this model is. So this is the model. Now we're talking about 1930. The concentration was about 300 ppm or so. Now, currently, our CO2 concentration in the atmosphere about 420, all right? So we are somewhere here. And if you look at his model, the increase in temperature, knowing that by his baseline here is 1930, so the increase by then, he didn't know that this, by the way, right? The increase by 1930 was about 0.2 degrees, okay? I'll show you where this is coming from. And you add this to his model, so he's roughly at 420 ppm, he's 1 degree, all right, for food. Now look at the other numbers that he showed here. In 1930, if you look at our measurement that we already know now, by 1930, concentration was about 300 ppm. So he's right on the spot here, right? His baseline at 300 ppm. The other thing that if you look at the cumulative CO2 into the atmosphere, where now we have much more data to count on, is if you like to take this data from our basic is coming in many places now, the world data, it is about 140 gigatons, and his estimate was 150. Okay, so this is by 1930, so he's really right on the spot. And now if you look at the average increase in temperature, now we have all this data. You can find, of course, there's a lot of fluctuation. You take averages, and overall we are about 1.1 degrees right now, okay, as of 2023. And more on that, if you look also in his prediction, because he said that you're doubling the CO2 concentration, right, from the pre-industrial level, the 480 something will increase the temperature by 2 degrees. We are not there yet, luckily, right? We're still at 420, so doubling, we're going to be at 560 ppm. So if you see 560 using some of the models here, you're going to see that temperature will be between 2 degrees and roughly 4.3 degrees, right? For it. So doubling the concentration, if you like, he's on the lower side, the lower estimate of our, could be one of the best models that we have. And for Arrhenius, on the other side, remember, he said doubling concentration would add 5 degrees. So Arrhenius on the upper side here. So take the average, both guys are actually on the spot here. All right, moving forward, other key landmarks in history is the creation or the establishment of the Mauna Observatory in 1958. And Charles Keeling takes a lot of credit for that, for establishing this observatory. And you find now when you go to NOAA website and you download this data showing the CO2 concentration. So now CO2 concentration is measured at daily basis, frequently. And for the first time, we could see actually a seasonal variation in concentration related to the summer and the winter, the vegetations and so on. So this is how the fluctuation is, or variation is happening here. So now we have very precise calculation. This is sort of at that location, right? But this is representing sort of average, as you see here, the blue line, average concentration of CO2. Now, on that, this is again, this was established 1958, right? But now when you look at the CO2 concentration, it goes so way back in history, right? Almost 800,000 years or so. So where these concentrations are coming from? Well, this is coming from what you call ice coring. Volker, he was just talking this morning about getting carbonate cores, right? So this is, we're talking about ice coring. And apparently Claude Lorry has a lot of credit, takes credit for, discovering this technology, if you like, or this observation, where he noticed that in the ice, drilling into the ice, there is some air bubbles that get entrapped there. Okay, and we thought that basically that air could be basically the historical air that got entrapped as the ice got created, or got formed. And this is basically moving on with this idea, and this is from Vostok Russian station, and where actually they got get a core 2,000 meters that aged to almost 400,000 years back, and from this data they could actually get a lot of information about from the air bubbles, right? Getting the air bubbles and measuring the concentration of CO2 in it. So they got a lot of data on it. And moving forward, now we have record of 800,000 years, right? And besides the CO2, you can get now a lot of other measurements like contaminants, dust, methane, and so on, right? So this is what we chose actually our 800,000 year history, right? So this now we're talking about the two combinations, right? So the measurement, direct measurement, and then the measurement from the ice coring that gives the history of CO2 concentration. Now moving forward, nowadays we have remote sensing using satellite-based measurement where we can get direct measurements, or not, meaning that at the actual time measurements for the whole Earth. The good thing about this, now we can get actually the concentration at basically at different locations. So you're not only relying on very specific spot to get it. I have just downloaded this movie. Let's see if I can get it from the from the website. All right. So this shows here actual measurements from the satellite, from the OCO. You can download this data, by the way, okay, for it. And this is the time here, from 20 to 2021, and it shows you basically what the concentrations. And this is the scale here, 400 ppm to 425. And you see how it's varying, right, from blue to red, right? Because, and of course, taking this data with some data, interpolations and assimilation and so on, you can get basically smooth estimate of the CO2 variation on the whole surface of the Earth, or whole atmosphere, right, around the Earth for it. And the other satellite that you can also access and get data from is Japanese greenhouse gas observing satellite, or the GOSAT. Also something similar, you get the data and it shows you the CO2 concentration over time. I think they show it at monthly frequency and stuff like this. So also you can get the data from it. All right, so this is talking about CO2, right? And then how we're measuring CO2 and different techniques, for it. Another, moving on with the key landmarks here is the establishment of the United Nations Framework Convention on Climate Change, or the UNFCCC, in 1992. And it got established on the basically goal to, it is the treaty to combat dangerous human interference with the climate system, in part by stabilizing greenhouse gases concentration into the atmosphere. The initial one was signed by 154 states. Right now, I think those who signed are part of the UNFCCC are maybe around 200 countries or so. And its headquarters is in Bonn, Germany. this is some from the archives of the UNFCCC. The first COP1 was in Berlin, 1995. And of course, probably you also heard about the COP27 that was just last year in Sharm el-Sheikh in Egypt. All right, now reaching net zero, where this net zero is coming from. I tried to go back and search really where's this first, if you like, usage of net zero and who started this. And the first one I found that has been used in a formal way is in the Paris Agreement in 2015. And this is what is the key, if you like, the key decisions or agreements in the Paris, in that agreement is to 3 points here: reduce emissions to limit temperature increase to 2 degrees, while pursuing efforts to limit the increase to 1.5 degrees. Review countries' commitments every 5 years. So these are what we call the NDCs. And there's some funding part to it for the countries who are trying to mitigate climate changes. And here they say that this framework marks the beginning of a shift to a net zero emissions world. All right, so this is basically apparent where this is coming from. Now I'm trying to find what's the definition, how they define the net zero, right, for it. All right, I came up with two definitions on it. The first one, it is a cutting greenhouse gas emissions to as close to zero as possible, with any remaining emissions reabsorbed from the atmosphere by oceans and forests and others. Okay, so essentially what we are saying, cutting almost to zero, as close to zero. The other definition is achieving a balance between the greenhouse gases greenhouse gases put into the atmosphere and those taking out, to some material balance. Right? So this one doesn't say getting to zero, right? You just need to have the net to be close to zero, while the other one is depending how you interpret it. But anyways, regardless how you define it and so on, I think it's a sort of, I think intuitive, right? What is needed to be done, right, on this aspect. All right. So coming back to the Paris Agreement, right, and learning more about it, is the what we call the CO2 budget towards meeting the Paris Agreement goal. So again, the Paris Agreement, there is one basically goal, which is trying to stay below the 2 degree, and then the other one is the pursuing the effort to stay below the 1.5 degrees. So there's 1.5 and 2 degrees. Okay. So regarding the 2 degree, that this is the first, the first goal here is that that we need to keep the emissions. We have to reach the net zero by mid-century. So this is to meet the 2 degree objective or 2 degree ambition. And the other one is to stay below 1.5 degree. Emission need to be cut by half by 2030. All right, for it. Very thick. Now, what does it mean cutting by half by 2030? Now, this is the emissions right now, right? By 2021 or 2022 or so, we are at the range of 35 billion tons of CO2 per year. Okay, this is the range. So thinking about this, by 2030, you need to cut this by half. Okay, to reach, to meet the target of the 1.5 degrees. Okay. Now, what if we continue emitting at this rate? All right, for it. If you continue emitting at this rate, this is what we call the budget for towards 1.5 degree. Continuing emitting at this rate, starting from 2023, we're gonna reach the 1.5 degree within 6 to 9 years. Okay, based on some this calculation. We're already at 1.1, guys. All right, so 1.5 is just, next by, right? So in bottom line here, the 1.5 degree goal is gone, right? It's no way, right, to reach this. Okay, now we have to think about the 2 degree, which is by 2050, right? Is the net zero by 2050 for it. Okay, for it. All right, so we're talking about 1.1 degree. This is average temperature. So what's 2 degree is already here. I think this paper published by Matalia and Tad. Saudi Arabia has already reached the 2 degrees, right? So locally, right, in some region, apparently temperature has already gone above the average, right? When you say average, meaning some places are getting hotter and some places are getting cooler. I think Iceland maybe are getting cooler, but another place getting hotter there. But miracles also happen, right? We're seeing this in Saudi Arabia, right? Just happened, and turning the screen and comparing this to Iceland, you can barely tell the difference, right? So Iceland is losing the, it's their competitive edge here. So yeah, we need to count on miracles here. All right, now moving forward from this and coming back to net zero, part of the Paris Agreement, what's the current world commitment towards net zero? You hear about net zero every time, all the time. So what do we have? There is this, something here called net zero tracker. They just track who's signed the net zero agreement or at least committed to the net zero and so on, right? Saudi Arabia already announced net zero by 2060, right? So it's one of these countries, and this is why it is green here. So all the countries except those in gray, there's few countries here, there's no commitment yet, all right, towards net zero. Everybody else here, they are at different stages of of announcing the net zero, okay, for it. And you can see them here. Countries, 132 countries already announced the net zero goals, okay, for it. This is by regional cities, companies, 800 companies or so. So you hear about many companies like Microsoft and others, right? They already announced, everybody wants to get net zero. Now, if you take all this commitment net zero, this represents 83% of current emissions. So that's huge. If everybody will meet their commitment, we're already there, right? We already cut emissions by 83%. Okay, for it. And this also represents 80% of population of the planet population there. So big commitments, it's clear there, big dreams. So let's see how we can achieve. All right, back to oil, guys, right? On this one, back to hydrocarbons, is where these emissions are coming from. So everything I'm showing here is emitting the 35 billion ton per year emission. This is coming from fossil fuels, all right? And it's essentially, we're using this as energy source. We have to burn hydrocarbons, essentially hydrocarbons and others, other sources. But if you look at the history of hydrocarbon or fossil fuel usage, this is from one of the BP's statistical reports here. They're showing you the oil, oil usage, and then others, gas, natural gas, and so on. But here, what you see here, what basically the point I want to show here is that moving forward, right, from 2020 or the current days, right, moving forward towards the mid-century, how are we going to actually take this, change, right? And everybody's trying to talk about energy transition, moving away or transitioning from fossil fuels, hydrocarbon to renewables and so on. Well, these curves are really very hard to push down, right? So there's no, you cannot have miracles to bring these curves down. So they have to be some transition, right, for them. And this one to transition down is going to take time, take major effort for this to happen, right? Look at this curve here. This is a renewable. And by the way, BP here, they call this the rapid scenario. So this is basically the most optimistic scenario they could come up with, right, for it, where renewables by mid-century can reach, let's say, 40%, 45% of the contribution to energy for it. The key line, of course, here, nobody knows, right? I'm not saying this is what will happen, but the key message here is that basically there's no magic here, right? So you need to go for transition. Hydrocarbons will stay around for a while, okay? It is really very hard to just say, drop hydrocarbons, just switch right away to renewables. This is not gonna happen, okay, for it. And of course, you want to push this coal, for example, the most, if not polluting hydrocarbon or fossil fuel to be replaced by natural gas that is maybe a little bit less polluting and so on. But this is the basically, regardless how you move this curve, by the way, things will not change much, right? If you push this up or down. All right, given that scenario, how would you get to net zero then? All right, for it. So this is now they're coming just with some scenarios, right, for it. What they're saying here is to get to net zero, somewhere down, you need to do different things. One of them, efficiency improvement. The other one, energy mix. So now you're including hydrocarbons, you're using less fossil fuels and so on. You're using CCUS, so carbon capture, utilization, and storage. And there could be basically room for other fuels like hydrogen, blue hydrogen or green hydrogen that could also play a role as part of the energy transition. This is also what they say here is this scenario that I showed earlier will give you, if you do all this, will say by 2050 at 10 gigaton per year emission. So even with that, the rapid scenario, you cannot reach net zero for it. And if you want to push this really further, you need to do even more from this one. So basically what they're trying to say is it's not easy task to do. Going look at others, Shell, for example, what they look at. So this is the Shell view for net zero. The current scene, this is what we're doing here. We're producing fossil fuel. We're emitting or we're generating 37 gigatons. 35 get emitted, about 2.6 get recycled, all right, or reused for something else. And for them, they see by 2070, maybe you're gonna reach something like this, where you still produce hydrocarbons, generating about 16 gigatons of CO2, but everything will be recycled back to be either used for other materials and chemicals. Okay. All right, how does it look like for Saudi Aramco here? Well, Saudi Aramco, they showed here this from their website, right? They have the circular carbon economy. It has basically been announced as a roadmap to reach net zero. By the way, Aramco has also announced net zero target by 2050, right, for it. So they have the net circular carbon economy, and then they also, have the CCUS as part of the, roadmap to reach this. This is CCUS, circular carbon economy. I think you are familiar with, which has the 4 R's and so on. I'll move quickly on this. But the key aspect of it is you need to have, carbon capture and storage is actually a key component of this roadmap. And coming back to Aramco, they just announced in the COP27, late last year, about this major project, which is a CCS project, right? The objective is to store up to 9 million tons of carbon dioxide a year by 2027, right? It's really coming close. So 6 tons will be coming from Aramco's facilities and the others from others' facilities. They will want to reach 45 million tons by 2035, and this will be somewhere in Jubail. 9 million tons per year. They will start at 9 million tons, yes. 9 million tons per year, yes. It's basically at this scale we're talking about. This would be maybe the largest CCS project worldwide at this time. Okay, for it. All right, now I want to highlight one thing here, talking about Aramco and net zero. What does it mean, net zero? So just to make sure we understand this, when Aramco says, or any of these companies, by the way, they say net zero, they mean actually net zero for their operations. Doesn't mean actually net zero for their produced oil. So produced oil is the problem of the client, right? Any oil that they sell, this is the problem of the client. There, they mean net zero their operations. Electricity they're using, the whatever fuel they're using for their pumps and so on, right, for it. And Aramco needs about, at this scale, they need 4 or 5 projects like this to get net zero, by the way, okay, for their emissions as operations, okay, for it. So it's not gonna be very hard for Aramco to get there, with this. But what will gonna be hard is, let's say whatever they're selling this hydrocarbon to a electricity company, for example, how this guy is gonna handle this, right? This is the problem, is the burned hydrocarbon and not the operation itself. So this is very, very, very tricky things to think about. Now, talking about operations, what does it take actually to, to produce? How do we produce oil? Well, this is on average we need to have 5 barrels of water to produce 1 barrel of oil. So oil doesn't come by itself. There is energy that you need to put, right, to get that oil out. You need to inject water, right? This is the most used method, and you need to put a lot of water there. Five barrels of water to get 1 barrel of oil. That's a lot of the introduced inefficiency in the system. And now when you look at the energy needed, right, to produce this oil, and in terms of the carbon intensity, how much carbon we're using or we're emitting to produce 1 barrel of oil. Now we see that 1 barrel of oil gives you roughly about, if you burn 1 barrel of oil, it gives you about 430 kilogram per barrel, kilogram of CO2. But if you look at the production itself, right, energy needed for production, is going to take between 20 and 200 kilograms of CO2 to produce 1 barrel of oil. And then if you add on top of it refining and transportation, this is basically, it gives you an idea how much it takes actually, or the footprint of 1 barrel of oil. Okay, there's CO2 coming from burning that barrel and CO2 coming from the energy used to produce that barrel. Now, why this can be this high, 200 kilograms? Because of other things that this unfortunate fact that the industry do, like for example, flaring to produce 1 barrel of oil, many places around the world, you get the oil and the gas, the excess gas, or you don't know what to do with the gas, you just burn it. So this is burned oil. This is counted here as part of this production. And also, as we mentioned earlier, a lot of water gets recycled to treat water and so on. So also this will add to the energy that you need to use for it. Now for Saudi Aramco, this is a paper by Aramco with Hussein Hoteit. They published this work a few years back, and they showed the carbon intensity around the world for all the oil fields and so on. You cannot see it very well here, but Saudi Arabia the second here in terms of the lowest carbon intensity, all right, for it, which is, probably not surprising, given that, the quality of the oil here and the oil fields and so on. So we are on the low side. The units here, by the way, are shown in the average in gram CO2 per megajoule. So you get it, if you want to get it in kilograms, you multiply this by a factor roughly of 6. You get kilogram per barrel. Okay, so roughly this will give you this numbers again. Okay, for it. All right, now back more on Saudi Arabia, and this is from the roadmap, right? Talking about the commitment and roadmap to get to net zero and so on and so forth. Saudi Arabia COP 2017. This is coming from the big screen from the Saudi Arabia pavilion there, and showing this electricity by 2030. The objective is, if you cannot read here, to get 50% from renewables and 50% from natural gas. Okay, by 2030. NDC contribution doubled, cut emissions by 278 million tons by 2030. All right. And then here, creating hubs for climate change, CCUS, cloud seeding, and so on. Okay, and I think maybe cloud seeding has already started to happen. I guess might be. And of course, there's others. Vision 2030, Saudi Green Initiative, circular carbon economy, and so on. These things that we talked about. All right, talking about the emissions in Saudi Arabia, right, and cutting emissions. How does it look like right now? This is a historical sort of view of the emissions in Saudi Arabia over the last 15 years or so. And it shows this in million tons per year. Okay, so right now we are at the range of roughly, say, close to 600 million tons per year. How much we're emitting, mainly from combustion of fossil fuels. Now, moving forward, if you would look at what are the, if you like, the milestones, right? For Saudi Arabia, there's 2 milestones there. There's the NDC. I just talked about 2030. We need to cut this by 278 million ton, and we have net zero by 2060. This is the national determined contribution for the Paris Agreement. So every country they volunteered or pledged to cut their emissions. Okay, and this is what it came under the NDC. All right. So how we go from here to here, right? You need to cut this scale, change really the slope really sharply here. Now, here, look what I'm saying. I'm assuming this is using the 2019 baseline. Apparently, we still have no clearance for clarity about what is the baseline when we say cutting by this based on compared to what baseline. Okay, for it. So this is comparing to the 2019 baseline, right? You need to cut this emissions. Of course, this will be again the plan to be part of the circular carbon economy, right? All the R's and so on for it. But this is just remember that this is a bit more complicated than this, because this also will depend about what do you call a baseline, okay, for it. So meaning that I can imagine that probably, somebody may think that they want to take credit for this decrease in the slope here, change in slope in emission. I say my baseline is this line. Okay, so by 2030, I want to cut emissions based on this line and not this one. So instead of being here, make big difference, guys. I need to be at 300 million ton per year using this higher baseline. Here, you need to be at 450 million ton per year. So you don't know how this is gonna be played, right? For it. So it's a very tricky thing. And then by this time you have to change something different, right? For it. So this is basically what I'm trying to say is whenever we say is the contribution or the NDCs and the plan to cut emissions, this is what they call it avoided CO2. Okay, so avoided CO2 meaning that avoided compared to the business as usual case, meaning that I would, if I do nothing scenario, I would be here at this by then. Okay, I'm gonna cut, right? I want to take credit for all this CO2 from the business as usual scenario down. Okay, for this, I would want to take more credit for it. In reality, actually, you're still actually on the high side here in your emissions. But this is just because there are a lot of lawyers there that played right on when they put things like this. So things are not what I'm trying to say. It's not that straightforward, right? When you say this number, right? What does it mean? Avoided CO2 and stuff like this, targets. So this is lot of details into it. All right, trying just to move quickly now. CCUS. I just mentioned one project Aramco is doing in deep saline aquifers, injecting this CO2. This technology has been sort of, well established in the industry, in the oil and gas industry, where CO2 has been used for enhanced oil recovery, has been also stored underground in depleted oil reservoirs, saline aquifers in many places around the world. But now moving forward, you see here there has been plans or to actually deploy many new projects in CCS. And the first one here is depleted in saline aquifers. You see there's a lot of interest now, many places around the world. And this is planned project, moving forward. There's in dozens of them. And they are mostly in saline aquifers here. Okay, what's the current scene now? What's the current status of CCS projects? Right now, we're CCS projects around the world, if you take the cumulative contribution, it's in the range of 40 million tons per year. All right, for it, 40 million tons. So if you give you this, just to give you what does it 40 million tons mean? 40 million tons is just this is 40 gigatons. Okay, so there is 1,000 times factor of 1,000 times. Okay, to be there. So basically, the contribution here of current CCS, we're talking about 0.1%. Okay, 1 per 1,000, right? For it. So we're still too far to have any dent actually on the what we're emitting right now. And this is where we need to be by 2050, right? I showed this earlier that CCS need to do really a lot, right, moving forward for this. It's still a long way to go. What is the major issues of CCS? Number one is cost. Okay, there's also other aspects like technical aspects and so on, of course, are still there. But the cost is really a key limiting factor here. It is still too costly. Capture is too costly. We're talking about something close to $50 to $100 per ton of CO2 to capture, depending on the technology and facilities. Direct air capture could be basically much more expensive, so depending what you do. And then there is transportation, the geological storage, mineralization. I know this is coming from old analysis. I know maybe from Carfix push this number lower with mineralization as technology evolves and so on for it. But this give you some rough idea that this is extremely costly. Okay, from capture all the way to the storage. All right. Well, other few minutes, I'll go really very quickly of what's happening here at KAUST. All right, for it, and how KAUST is trying to, if you like, to contribute to the solutions of this major challenge. So one of the initiatives that KAUST has right now is the Circular Carbon Initiative. You see here in this illustration or cartoon here, it has the 4 R's, which is essentially inspired by the CCE. All right, for it, and there's different thrusts there. The first one is the CO2 capture. This led by Bill Roberts and Mohammed Dawoodi. So Dawoodi works on direct air capture. Bill Roberts working on cryogenic CO2 capture. And by the way, this has been announced also one project between KAUST, Ministry, and Saudi Electricity to capture CO2 from one of the power plants in Dubai. So using this technology. We have also nature-based solutions from Duarte, Professor Duarte, and McAfee also. And then, of course, we have geo-based solution with Thomas, and has different. So each one here have different projects, all right, embedded in it. Okay, maybe 5 or 6 projects in every trust here. Okay, the e-fuel working with Gascon and Serate work on hydrogen, catalyst, and so on, and the cross-cutting with DeWolf and Daly working on renewables and other things. All right, I don't know how much time I have, but I'll go just maybe one slide per project, just to give you very quickly what we're working on. So this one major project we're working on with Professor Afifi here, trying to assess the storage potential of the CO2 in the different formations, in saline aquifers, in depleted oil and gas reservoir, and so on, and also has some aspects to look at the emissions, where they are coming from, and so on. This is, if you like, similar to what we call the Atlas, CO2 storage Atlas that has already been developed for many different countries around the world, like North Americans and Norwegians. And with this, we have looked at the emissions, surface emissions, where they are coming from, mainly from the facilities. So this point source, okay, industrial facilities, and put them in the map. And you see here, for example, Jubail that I talked about earlier, right? It's a major source for CO2. It is a major industrial cities, so you have a lot of emissions coming from. And then we have cluster in Riyadh and others in Yanbu, Rabik, Jeddah, and Jizan. Okay. We have this paper, by the way. It is we have all the data, the raw data we put there. If anybody is interested in this, we have a lot of other information about the emissions that I can skip for now. We also look at building on some geological models, like specific sites. Look at building the geology and looking at the getting some subsurface information, running some simulations, and so on. And then there is another major project that we're also excited about, is related to CO2 mineralization in basalt. So this has been inspired by the early work that was done in Iceland, where they showed that you can inject CO2 and water and try to accelerate the mineralization of CO2 underground. So you're turning CO2 into rock, into carbonate for it. And there is now ongoing work. So Professors Olkers, Eric here, and Sigi are here, actually, working together on We're looking at the potential of basically deploying this technology and understanding the feasibility of this technology in different volcanic fields around in Saudi Arabia, mainly along the west side of it. And this is also one project that hopefully will be, get into the ground at some point, which is to drill a geothermal well here at KAUS. Still at the planning stage, but we have a lot of support coming right now from KAUS, and hopefully this will be realized. The idea here is to drill what we call low enthalpy geothermal. So this is not for, we're not going to get steam here or something. This is just hot water that could be used for desalination or usage for like cooling and heating and so on. So this is still ongoing. Also, with Volker, he's working on even extending this idea, going from just a traditional geothermal to include CO2. So this is where CO2 is coming in. That you can probably use the CO2 as a carrying fluid instead of water. All right, just to wrap up, what's the key takeaway from here? Again, this could be biased here on this, but this is how it looks like. Hydrocarbons are not going away soon. They are still our friends. Energy transition is a necessity. No way back. I think people are still skeptical that this is just a bubble, will go away. It's not going to go away. All right, for it. So as long as we see all this, the impact, right, of climate and so on us, this will keep reminding us that this is serious. Right, for it. Net zero targets could be too ambitious. We need more, maybe scientific, also grand truth planning associated with this. What is feasible, what's not only, big dreams. Global commitment is needed. It is still missing right now from all around the world, right? This really requires everybody to contribute, from government, from politics, policies, companies, people, us. Very challenging problem, a lot of opportunity in front of you guys, all of us here. And with that, thank you very much. I'm happy to take any questions.